These are the straight chain hydrocarbon notes. You should have already watched this What is Organic Chemistry video and completed the worksheet to get a little bit of basis for that introduction to organic chemistry. And in that video, you should have learned that hydrogen and carbon are the backbone of organic chemistry. And so as we are looking at a kind of just brief understanding of what does organic chemistry look at, we are going to look at straight chain hydrocarbons, and we're also going to look a little bit at functional groups. And so straight chain hydrocarbons, this is if we have any, and again, hydrocarbons, hydrogen and carbons. If we have any amount of carbons, these are going to be organized in a straight chain, whether we draw them as a straight chain. So let's say we have 5 carbons or 4 carbons, if they're organized like that, or if we have those 4 carbons and maybe it shows that there is a bend, but all of those carbons are connected in a chain, that is those straight chain hydrocarbons. Why are these the backbone of organic chemistry? Well, carbons want to bond 4 times. They need 4 more valence electrons. And so if we look at a chain of carbons, we have these all connected to one another. Well, hydrogens have, so carbons have 4 valence electrons, which means they want 4 bonds. And so they can easily bond with other things. Well, hydrogen then has 1 valence electron. It only wants 2 valence electrons because of its energy level. And so it only wants 1 bond. And so we can have all these carbons that are connected, and then we can fill in those hydrogens wherever those carbons need that additional bond so that all of these are happy. So we've looked at some of these at the very beginning when we were looking at drawing covalent compounds, but we didn't really use the correct naming for those that follows the organic chemistry type of naming. So that's what we're going to start to look at in these notes. So when we are naming, we maybe had called this tetracarbon, but that's not actually how organic chemistry does naming, because we know that carbon is the basis of those compounds, and we know we're going to fill hydrogens in either way. So we don't need to say tetracarbon and then what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decahydride, but we know that those hydrogens are going to be there to kind of fill that in. And so we do have different naming conventions when we look at naming hydrocarbons. And the first thing we're going to have is our prefix. It's going to tell us the number of carbons that are in a chain. And these prefixes are different than those prefixes we were using just for covalent naming. And these are provided on your pink formula sheet, so you don't have to rememorize these. They're on the formula sheet for you. And so if you only have 1 carbon, that would be meth, and then those go up. So eth, prop, but, pent, hex, hept, oct, non, and then dec. And so some of these we've seen before, but some of those lower ones are easier, the lower ones are different. So we have a prefix that's going to tell us our number of carbons. Our suffix then, what's going to come at the end, is going to tell us the type of bonding. And so these carbons are connected in a straight chain. They can be connected with all single bonds, and that is called an alkane. And those are called saturated hydrocarbons because it has all those hydrogens surrounding it. And the molecular formula, if you have an alkane, so if we're looking at a molecular formula, we could see that if there's a relationship between the number of carbons N and the number of hydrogens, 2N plus 2, from just that molecular formula, we could tell that that was an alkane. If we have a double bond somewhere in the chain, then that is called an alkene. The molecular formula, because of a double bond, it means we're going to have a few less hydrogens. So instead of N carbons and 2N plus 2 hydrogens, we're going to have N carbons and only 2N hydrogens. And then we have alkynes. And again, this is kind of pronounced I-N-E, even though it's spelled with a Y. And that means that there is a triple bond somewhere in the chain. And again, if we have a triple bond, we need even less hydrogens, making those carbons happy. So it's going to be N carbons and 2N-2 hydrogens with those. And with our alkenes and our alkynes, we're only going to have one double bond or one triple bond in that chain. So if we have four carbons or more, we use a number to state the location of that double or triple bond so that we know exactly where in that chain it is. So if we look at these, let's write the molecular formula using that relationship between our carbons and our hydrogens. We're going to need to look at our prefixes. So if you need to, grab out your formula sheet. Those are on the back side in the bottom left corner. And then our suffix, again, we're going to have to kind of compare those to our N values, or we're going to write it based on the rule for each. So looking at this first one, we have prop, and that prop prefix is telling us that we have 3 carbons. So prop means 3 carbons. Ene, well, ene means we have a double bond at some point. And so my carbons, if I have 3 carbons, I'm going to have 2 times 3, 6 hydrogens. So this would be C3H6 is the molecular formula. Decane, that prefix dec means 10. So that again is from our formula sheet. So that means we're going to have C10. Ane means that all of those are connected with only single bonds. And so that relationship is going to be that our hydrogens is going to be 2N, so 2 times 10, which is 20, plus 2. So this is going to be C10H22. If you want, go ahead and try the next couple on your own. We've got heptine. So hept is 7, C7. Again, that's coming from our prefixes. That's telling us our number of carbons. Ine means there is a triple bond somewhere, and in those 7 carbon chain, so we're going to have 2N, so 2 times 7 is 14, minus 2, so H12. C5, H10 is our next one, pent is 5, and then that ene is, again, our 2N, so H10. And with this, those 4 or more carbons, we should have a number on these 3, and we would put that something like 2, nope, not decane, because that only has single bonds. Sorry. We could do like 2 heptine. That would tell us that the triple bond is coming out of the second carbon. That pentene, we could say 2 pentene. That would tell us the double bond is coming out of the second carbon. I didn't add those on there, but when we are naming them correctly, that is what we would do. All right, writing the name, C4H8. Well, having 4 carbons means I'm going to have bute as the prefix. So we have bute, and then looking at what is our relationship, well, if N is 4, 8 is 2N, which means we are looking at that N-2N relationship. This is an ene, so butene. C8, H18, 8 is oct, so again, that's from my prefixes. Looking at this, 8 times 2 is 16, so this is 2N plus 2, which is going to be an alkane, so octane is that compound. CH4, 1 carbon, that's a prefix of meth. Well, 1 carbon times 2, so 1 times 2, or 2 times 1 is 2, but we have 4, so plus 2, that is also an ane, so methane is that CH4. And then C2H2, C2, that is eth. And then when we look at that, I have 2 times 2 is 4, but to get to 2, I need to subtract 2. So that is going to be ethine. All right. So when we are taking that name and writing the molecular formula, it doesn't really tell us a lot about the structure. And if I knew where my triple or double bond was, that's where that number in front for the name would tell me that. These ones, this butene, we'll look at why we wouldn't necessarily need a number on that one because it is or actually this one we would need because there's 4 carbons. But this ethene, we would not need a number on because we don't know, because there's only one place that triple bond could be. So we are going to now go into looking at some more complex or at multiple ways to represent our hydrocarbons. Now that we can kind of know, we know what things we're looking for in our chain. We're looking at, is there a single bond only, double bond, triple bond? We're going to look at different ways we can represent those hydrocarbons. So we have the name, we talked about that, and we have our molecular formula, which is what we were looking at earlier. And we have those kind of molecular formulas, those ways we can identify what type of bonding there is based on the molecular formula. And a molecular formula shows the number of each atom present. There's no information, though, about the type of bonding. And so we just list all of our carbons and then all of our hydrogens, kind of grouping everything together. But if we have something, this is 1-butene, I can't tell where, if this is butene, that means that there is a double bond somewhere in my chain, and I can't tell where that is just based on my molecular formula. So we also have a condensed formula, and that is where each carbon atom is listed separately, and then the atoms that are attached to it follow that carbon. The name condensed formula, it comes from us being able to see the structure without actually having to draw out the structural or the displayed formula. And so it allows us to not have to make a huge drawing, but we can still showcase what we have going on here. And so the condensed formula for this is CH2, CH, CH2, CH3. And notice we have 1, 2, 3, 4 carbons and 2, 3, 4, 5, 6, 7, 8 hydrogens. It's just now this is telling me how this is organized. And this can help me then easily transition to looking at my displayed formula, which is similar to our Lewis structures that we've had. And this shows all the atoms and all of the bonds that are present in the compounds, shows all the atoms and all of the bonds present are drawn with that. And so as we look at this, this is the displayed formula. And one note with this is that we have all these hydrogens here because we know those carbons are going to bond with hydrogens to get to their octet. We actually don't have to put in the hydrogens. And I couldn't find a picture, or maybe I just didn't crop it correctly, that actually the displayed formula, a better way to showcase that would be to show, here's all my carbons, and then I just put a line showcasing where each of my hydrogens would be. And so here we can see, here's my C2, there's that first group, and then on my next carbon, I have just 1 hydrogen. On my next carbon, I have 2 hydrogens, and then on my next carbon, I have 3 hydrogens with that. And how do I see the name? Well, this is 1-butene. But means 4, ene means a double bond. Well, this 1 means that the double bond is after the first, or is coming out of the first carbon. And so this is where we see that 1 come into play, 1-butene, and that is where, or what carbon is the double bond after, like that. And so that's what the number helps us to say. And we can count this, we can count and say this is carbon number 1, 2, 3, 4. And we are always going to count to make it so that it is coming out of the least or the smallest number of carbon. It would not be correct for us to look at this one and count it and say this is my first carbon, this is my second carbon, third, fourth. Naming this as 3-butene would not be correct because we always want our numbering to go from, so we number, so carbon, or so bond is at lowest number possible. And so we can start our numbering from either side based on how our structure is drawn, like that. All right, and so this displayed formula would actually be more correct without the hydrogens. And we'll see if I remember to update that on your notes with that. All right, and then lastly, because again, having to write out all these carbons and all these lines, it does end up being a lot of work showing all of those atoms and the bonds that are present. So we also have a skeletal or a line formula, and the line ends represent carbons. And so if we look at this, we have 4 carbons, because again, that prefix but means 4. And so where do I see those? Well, here's 1, 2, 3, 4. The line ends represent our carbons. So that's how we see we have 4 carbons. And then we are going to draw on our functional groups, and atoms other than carbon and hydrogen are shown. So this only has hydrogens around it, so we don't see any of those hydrogens, but I do then see my double bond after my first carbon by having that second line there. And again, this is my first, second, third, fourth carbon. I'm always going to label it so that my double bond is at the lowest spot. So it's after the first carbon. It would not be, if we said 1, 2, 3, it would not be after the third carbon with that. So these are the ways we're going to look at representing the name. The molecular formula just chunks everything together, but our condensed formula allows us to list out the structure in a form where we're not drawing it, but we're able to see how everything is organized. Our displayed formula is showing all of the atoms, and our skeletal formula is going to simplify that down to the lines. We're not actually having to draw out the carbons either. All right, let's try a few. So these ones are broken up into our types of bonding that we have, and then there's a couple at the end where they are mixed. So looking at these are the anes, which means that we are going to have just single bonds in the chain. So we don't have to worry about a number saying where that bond is. And then for our molecular formula, we're able to use that CN, H2N plus 2 to look at that. As we're looking at these, you might want to start with the molecular formula, which is using that kind of formula that's there. You might want to start with drawing out your displayed formula to figure out what that looks like, or to kind of like gather what you all have here. So if we were to, let's say, start with our displayed formula, prop, well, prop means I'm going to have 3, so this is C3. So I'm going to start with a chain of 3 carbons. I know that because of this ane, those are only single bonds. And so we can, from there, I know that I'm not going to have to add any double bonds, and I can make the rest of my carbons happy by adding hydrogens around there. And so this is my complete displayed formula. If I want to look at, well, how many hydrogens am I going to have? H, I have 1, 2, 3, 4, 5, 6, 7, 8. Each of these represent a hydrogen. We just don't have to draw that, so H8. And we should be able to check, well, 3, well, 2 times 3 is 6, plus 2 is 8 with that. So there is our molecular formula and our displayed formula. Our condensed formula then is going to explain the structure. And so we're going to list each carbon at a time. And so my first carbon, looking at this one here, I have 3 hydrogens on it. So I'm going to say CH3. My next carbon now, I have 2 hydrogens on it. I'm only looking at the hydrogens, not at what else, not at the carbons being attached in the chain. So CH, that has 2 hydrogens. And then my last one, we've got that last carbon is going to have 3 because it doesn't have anything else on the side, so CH3. And that is my condensed formula. I can see the structure and what is on each of those, but I don't have to draw that out. So we've got our molecular formula we've got our condensed formula, our displayed formula, our line formula now. I'm going to put my pen down, and every endpoint of a line is a carbon. So here's one carbon, and then 2 carbons. I need a 3rd carbon, and so it's going to look like this. So we do these little zigzags just so we can see. And here's my 1, 2, 3. Those are my carbons, that first one, that second one, that third one. And we don't draw any hydrogens. We know that the hydrogens are there to make our carbons happy. All right, nane, if you want, try this one on your own. Non is 9, so C9. This is an ane, so I know that my H's, it's going to be 2 times 9, which is 18 plus 2. So I'm going to have C9H20. I think it is easier to draw one of my formulas before I write my condensed formula, but you could go ahead and write that out. So I'm going to need 9 carbons. 1, 2, 3. You can see why, if we have these long chains, why those displayed formulas take up a lot of space. And then making each of those happy, so adding those hydrogens. The ones on the end are going to get 3 hydrogens because they don't have carbons on 2 sides, and then the rest of them end up with 2 carbons, or sorry, 2 hydrogens, because they have 2 bonds, and so there's 2, 3, 4. Now carbon is happy with that. So there's my nonane displayed structure. I could go ahead and count those lines to make sure that I have 20 hydrogens on there. For our line formula now, those line formulas are beneficial because I can just go 1, 2, 3, 4, 5, 6, 7, 8, 9. And each of those endpoints, 1, 2, 3, 4, 5, 6, 7, 8, 9, represents a carbon. I'm not needing to draw the lines or draw those hydrogens. And so this allows me to see the structure in a visual way without having to maybe write as much as the displayed formula. Our condensed formula now, as we look at it, we can write that out. I have that first carbon, this one right here, and that has 3 hydrogens, so CH3. And then I have my next one, CH2, and I can go ahead and list. I'm going to have that CH2. I'm going to have 1, 2, 3, 4, 5, 6, 7 of those CH2s. So there's 2, 4, 6, and we need 1 more. Oops. So there's 7 of those. And then I need another CH3 on the end because that last carbon is going to have those 3 hydrogens as well. And so I can write it out like this, but that condensed formula is not very condensed. But we do notice that all of these CH2s, 1, 2, 3, 4, 5, 6, 7, all 7 of those on the inside, that's that same thing. So we can actually condense this even further. You could write that first part out, or we could say, well, this is CH3, and then that's CH2, and I have 7 of those. So if it's that same part repeated, I can put that 7 after there, and then I end it with that CH3. This still allows me to see the structure, but I'm not having to write all of those out. I can just say in parentheses after that group how many of those I have, and that represents all of these carbons that are in this piece. All right, let's look at some alkenes. Ene now means that we have a double bond somewhere. And so we are going to potentially have a number that's going to tell us where in that chain the double bond is. So for decene, and that molecular formula is right here. So we have des, that is 10, so I'm going to have C10, and then H is 2N, so this would be H20. If I'm now looking at it, my molecular formula doesn't tell me where that double bond is. So that's one thing about the molecular formula that's not nice. Let's look at our displayed formula. We are going to have 10 hydrogen, sorry, 10 carbons, 1, 2, 3. So I've got 10. And now, what does this 4 tell me? This tells me my double bond is going to be coming out of the 4th carbon. And I could start this as my carbon number 1. I could also start this as my carbon number 1. Whatever way you prefer, you can start your numbering. I usually go left to right. And that means that if this is a 4, that double bond is going to be coming after our 4th carbon. And how we remember it is because it can't come before our first, so it would have to come after our first. So it's going to have to come after our 4th carbon. So this is my 1, 2, 3. Here's my 4th carbon. That means that that double bond is going to be after my 4th carbon between my 4th and my 5th. And so that's how I know where that goes based on my numbering. And now I can go ahead and put my hydrogens on. That first one has 3, this one has 2, this one has 2. But now that this carbon has 3 bonds, it's only going to need 1 hydrogen. Same thing with this one. It already has 2 shared electrons here, 1 here. It can only have 4 bonds, so I'm going to put that there. And then these ones get their 2. That end one gets 3, so that everyone is happy with an octet. I put these above my carbons. You could have easily put them below. It doesn't matter where you are actually putting that hydrogen, but each of these needs 1 of those hydrogens. So this is my displayed formula. And again, it's pretty long. And so when we have those larger formulas, having the line formula is going to be a little bit easier to draw. I'm going to have 10, so I put my pen down and I need 10 endpoints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my 10. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then again, let's show our double bond. Well, that's going to be after our 4th, or out of our 4th carbon. Here's 1, here's 2, here's 3, here's 4. So how we show that double bond now is after that 4th carbon and between that 5th, we just put another line to show, because this represents a single bond. So now we have another one that represents our double bond. There's my skeleton or my line formula. My condensed formula is how can I write this out to show the structure of where that double bond is. And so I've got CH3, and then I have CH2, CH2. So I'm going to combine those. CH2, I have 2 of those. That represents these 2. Now I have carbon with 1 hydrogen and another carbon with 1 hydrogen. And so I'm going to do that as CH. And I have 2 of those. And then I have 1, 2, 3, 4 more CH2s. And I have to put those, I have to separate these because I'm listing the structure of my chain. And then I have that last CH3. So that represents our very last part of our chain. And I could go ahead and list each of these separately. Oops, this was supposed to be a CH2 too. There we go. I could list each of those separately, but that is going to just take up more space. But here's my condensed formula. Maybe on a shorter one, I'll write it all out. All right, if you're feeling comfortable, hop in and do 2-hexene on your own. It's another ene, which means there's a double bond. That double bond is going to be in that second spot. So hex, looking at our formula sheet, is 6. So 1, 2, 3, 4, 5, 6. 2 means that that double bond is going to come out of our second carbon. And I could start my numbering here if I want, and put it here, or I could start my numbering on the other side, 1, 2, and it could be here. Either way, we are going to number, we can number from either side, and if it is flipped, if your structure is flipped from maybe someone else's, it means the same thing, because we're going to number it so that that double bond is at the lowest numbered spot. So I'm going to go this way. So there's my 2 hexene. There's where my double bond is. And I'm going to make everyone else happy. That carbon needs to get to 4 bonds. So there's 1, so it needs 3. This carbon, 1, 2, 3, so it's going to need 1. 1 hydrogen here. This one now needs 2, 2, 1, 2, 3, 4, like that. So if I was to write out the condensed structure, CH3, that is this first one. And then we have CH, that's this one. Then we have another CH, that's this one. And then I have a CH2 and another CH2 and a CH3 with that. So there's that kind of fully written out condensed structure. And just like we did on that other one, we could condense some of these groupings further. I could take those groupings that repeat, and I could say I've got CH3. These two repeat, so I could say CH, and I have 2 of those. And then I have these 2 repeat. You can say CH2, and I have 2 of those, and then I end with a CH3. So either of those 2 are appropriate for that condensed structure. You could see it either way. My line formula, I have 6 carbons, 1, 2, 3, 4, 5, 6 endpoints, and the double bond is coming out of the second carbon, and so that's going to be here if I'm labeling from the numbering from the left. My molecular formula is going to be C6. And I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can also look, what is that? So I've got 6, so 2 times 6 is 12, so that looks correct. I can also make sure I add all those up, and that's correct, so that H12 is the rest of that molecular formula. All right, let's try a couple of these alkynes. If you want, go ahead and try for nonine on your own. Let's start with the molecular formula. We know that for non-ines with the triple bond, it's going to be whatever our N is, our H's are going to be 2N minus 2. So we've got non is 9. So then my H's are going to be 2N, which is 18 minus 2. So C9H16. I'm going to wait on my condensed formula until after I have my displayed formula, but feel free to try that one next if you want. And then 9, we're going to have 9 carbons, 1, 2. And then that 4 means my triple bond, because those ines, my triple bond is going to be after or coming out of the 4th carbon. So 1, 1, 2, 3, 4. There's my triple bond. I just show that with the 3 lines in between. And I'm going to make everyone independently happy with so each carbon is sharing 4 times with something. When I get to my carbons that are in my triple bond now, they aren't going to get any hydrogens because they are sharing 3 times with their carbon that is next to it. And so just making sure you have the correct on there. So there is my displayed formula. To write my condensed formula out, I've got CH3 for this first one. Now I have 2 CH2s. So CH2, 2. These ones do just have carbons, so we could say C2. And then I can say CH3, nope, CH2. And I have 1, 2, 3 of those. So I'm going to do parentheses there, and then ending with a CH3. And I could write all these out or grouping those repeated groups. Our line formula, we're going to put our pen down. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. My triple bond is going to be after my 4th carbon. So 1, 2, 3, 4. And we are going to put 2 more lines there to show that is a triple bond. Try pentine on your own and then come and take a look. We have got the molecular formula, the condensed formula, it does look a little weird because these carbons don't have hydrogens because they're triple bonded. And those are there as well. This one, 1, 2, 3, 4, 5. I drew my 2 lines, so each one represents another bond. So there's my triple bond. I drew these ones on opposite sides of the original line. You could do them on the same side like I did up here. Either is fine. All right, go ahead, try these next 3, pause the video and come back to take a look. Reach out if you have any questions on those. And then we are going to just talk about a few more things. Isomers are compounds that contain the same part but are arranged differently. So kind of like a pile of Legos can be stuck together in different ways. We can have a bunch of carbons and a bunch of hydrogens, and we can stick those together differently. So you must have at least 4 carbons for an isomer to be possible. So a different arrangement of the same parts. And why would that be the case? Well, the reason why in something like our 2-hexene, I have 6 hydrogens. Well, I could put my double bond here, and that would be a different configuration. That would be 1-hexene, or here, or here. I can't put it here because then I would go 1, 2, and that would be the same as this original structure we drew, because we number so that they are always going to have the lowest possible numbering. And so why is this the case? Well, we need enough options to rearrange. And so if we are drawing it looking like they're not in a straight line, that doesn't actually give us a different to rearrange. That doesn't actually give us enough options. And so things like meth with just 1, eth with 2, prop with 3, those don't have enough options because if we have a double bond, it can only go in one spot based on our numbering or any of that. So isomers, we have different ways we can draw things, but there are certain things where we would only end up with one configuration. So let's look at butene. How many ways could we draw that? And if you want, go ahead and give this a try. Butene, well, but is 4, and then our ene is going to tell us we have a double bond. And I'm going to just draw out my 4 carbons here, and then I'm going to look at, well, where could I put that double bond? And I could put that double bond here. So that would be one option. And that would look like this, with all of those carbons happy. But I could also move that double bond, and I could say, well, I'm not going to put it here, I'm going to put it here instead with that. And as we look at these, this first one is 1-butene because that's coming out of our first carbon. This one is 2-butene because now our double bond is coming out of our second carbon. As we look at something like this, if I move my double bond down one more, let's say I put it here. As I look at this, 1, 2, 3, after our third carbon, 3-butene, we need to make sure that as we're numbering it, our numbering is that as low as possible. I actually could number from the left, 1, 2, 3, 4, and this would be the same as our 1-butene. And so 3-butene is not possible. We number, if we even have to number backwards, we always want the lowest numbering possible. And it might mean we are numbering from the right side and numbering those backwards like that. So these are actually the only 2 ways we can draw that 1-butene, which is those 4 carbons with a double bond somewhere in the chain. And those are the only straight chain isomers. There are other ways you can put those parts together that aren't in a straight chain, but we are actually not going to talk about branched isomers this year. All right, take a minute, maybe try this one on your own. Why is 6-decene not possible and what should it be named? I'm going to go ahead and pause and I'm going to draw this out. Why is 6 decene not possible? I counted from the left, 1, 2, 3, 4, 5, 6, and I put my double bond after my 6 carbon. But kind of what we talked about, we want to, if possible, label so that is the lowest number. It's at the lowest numbered spot. So because decene, that's 10, we're not going to ever have a number above 5 because we would rather make this my number 1, 2, 3, 4, and this is 4 decene and not 6 decene. So as we talked about above, we want that lowest number possible. And so anywhere over the halfway point is not possible. We can number our carbons either from left to right or right to left. We just want it to be the lowest possible number. There is a worksheet for practice. Please reach out to your teacher with any questions.